All right, gentlemen, these notes are on chapter 3, so we're starting a new chapter in the textbook now. These notes are posted for you to annotate down with me if you'd like. They are from, exponential, so e and exponent, things like that, and then we're going to do the inverse of that, so logs. There's a little bit in here about logistic too. We'll do a little bit of that, but we'll kind of focus more on the first two just so this video doesn't get too long. Alright, so as it says here, there's a difference between functions being something like this, where it's x squared, versus it being 2 to the x, right? One of them is a power function, where the base is the variable x, and the power is a constant, where it's a certain thing that changes, but that's always being squared. 2 squared, 3 squared, 4 squared. The other one is an exponential function, 2 to the x, where the base is 2, the constant base is 2, but the power changes, so 2 to the second, which is 4, 2 to the third, which is 8, 2 to the fourth, which is 16, right? So it grows at a slightly different rate. Okay, so as it says here, a and b are real numbers. An exponential function is x, a function that's written in this form, right? So the thing we need to know from here is the variable is the exponent or the power, right? So the variable's the power. Usually we see like x squared where the variable is the base. In this case, it's the other way around. And a is the initial value. A is the initial value, meaning where you start. If I were to plug in 0, I would get what? I would get a, right? And it kind of makes sense because a, b, x, right? If x is 0, a times b to the 0, that's the same thing as a times 1, so you get a. So that's your initial value if I plug in 0. Just looking at this, do we know if it is or is not an exponential function? Yes, this is exponential. The base is a constant 3. The exponent is the number. X is the variable x. The second one, 6x to the negative 4, well, this would really be 6 over x to the 4th, right? And this one would not be exponential, so this is not exponential. Not exponential, because when you write it like that, the base is the x, right? The base is the x. The power is the 4. And you're really solely looking at the fact that is the x the power or is the 4 the power? This one, yes, exponential. Right? It's kind of in that form we see up here. It's in this form, negative 2 times b to the x. B to the x, 1.5 to the x. The initial value here, initial value is negative 2, because if I plug in 0 for x, that'll cancel out the 1.5, it'll just make it a 1, and my initial value is a negative 2. And this one, there's no x in it at all. It's a pi, a 6, and a 5, so this is just a constant number. So this is really not exponential. It's not a regular power function like this one. This one's a power function where it's x2 power. This one is just a constant number. It's a constant. Although it's irrational, it has pi, it's still constant. All right, so just a little bit of understanding of when we have an exponential function, what does it look like? It's raised to the x. The x is the exponential. All right, so looking at the next one, just playing around with it, 2 to the x. So let's plug in different variables for x, right? So if I have 2 to the 4, 2 times 2 times 2 times 2, 16. Very simple. 2 to the 0, that gives me 1. Little review of stuff we had done in the past, and that's kind of why your initial value is the a, the number timesing the b to the x. 2 to the negative 3, 1 over 2 to the 3. Little review from what we had done in the first trimester. Negative exponents means you got to put it in the opposite side of the fraction, and this is 1 over 8. 2 to the 1/2. This was from kind of a while ago. 2 to the 1/2, that means it's radical 2. Really, basically what it's saying is you have like 2 to the first, and this is a 2, right? And we don't see the index of the radicand, we just assume it to be a 2. So, and if we don't see a power to this number, right, we don't see the 1 there, we just assume it to be a 1. So 2 to the 1/2 is a radical x. Okay, so let's just review on how to plugging in those numbers. Let's look at the graph of b to the x. So I had graphed this earlier. It should come up here. There we go, b to the x. B being the constant number. Let's look at what happens if I hit this little slider button. It's going to fluctuate between -1 and 5. So if I hit play, let's watch what happens. Okay, so it's going down, right? So it's at high values like 5, 4, 3, right? Like big numbers. Now it's going down from 5 to 4 to 3, and now it reverses, right? And let's kind of watch that as this is live. Right? So here, my b value is 5, my base is 5, and now it's coming down to 4, it's going towards 3, towards 2, right? We see it gets to 1, and then it kind of flips the other way, and then it gets 0, and it just cancels at negative numbers, right? So this can only be positive for it to have some form of a graph. So it gets very interesting. So let's just talk a little bit about what does this function mean, right? So looking at that graph, the basic function b to the x, it has a domain of -infinity to infinity. Right? We saw it went everywhere. If we pick any particular value for b that I'm allowed to, I can really pick any number. When it goes backwards, it gets a little bit weird. My range is 0 to infinity, right? It started at 0 and it never really changed. It never really changed from that, right? We see here. Right, it never passes 0. It never goes lower than 0. Okay. It's continuous. We saw there was no gaps in there. There's no problems with it being like a fraction of sorts, and there's no thing that we can't do when it's a power of a negative or anything like that. That's all fine. It's continuous. It's bounded below by, right, x or y equals 0, right? It never goes lower than 0. Okay, there's no local extrema. There's like a horizontal asymptote at 0. There's no vertical asymptote. It kind of just continually gets closer to asymptote, but not fully an asymptote. Right, so those are just a couple facts about what the graph looks like, right? And if we just go like this, we'll just kind of pause it at a nice looking one. I'll just pause it right there. Screenshot this. And we'll pop this into the notes, photos. And there's my photo of it. And so there's what my b to the x looks like, something like that. Okay, we can use this, what's the use of this? We can use it to kind of define recursive things, right? I'm multiplying in this function g to the x. I'm multiplying by 3 every single time. First, you want to find what's your initial value. So your initial value is when x is equal to 0. So for example, here, I look here. When x is equal to 0, I have the number 4. And so 4 times, now what am I multiplying by each time? 3x. Right, so there is my that's my like recursive function g of x. 4 times 3 to the x. All right, how do I know it's that? Because 4 is my initial value. I'm multiplying it by 3 every time. How many times do I do it? Well, how many x's do you want? You want 0 or 1 or 2? H of x, same thing. I'm starting with the number 8. There it is. I'm increasing by 1/4. I'll actually write this a little bit more clear. I'll do times like this. 1/4. And I'm going to do that x times. How many times do you want to multiply by 1/4? Well, you tell me. This is the number of times is my x, right? Multiply from my original twice, or from my original once. Right? So that's the idea. That's how we use it in the form of recursive, where you find your initial value when x is equal to 0, find out what you're multiplying by each time, and then the variable is how many times are you going to multiply by that number. Just like if I were to say add 3 to this number every time, you'd be like, oh, that's multiplying. The step up from adding is multiplying. The step up from multiplying is exponentials. Okay, we can see that g of x increases by a factor of 3 every time, g of x increased by 3 every time, and h of x increased by 1/4 every time, right? So that's my b value, my base, and the x is, well, how many times does it increase? Here's the general form right here, a times b of x, right, where I have right here a, timesing it by b, and this is the number of times I'm going to multiply it by b. And it just says here a times b of x. That's my recursive form of an exponential, and it's used to define growth or decay, right? So it's like carbon dating, basically. Okay, so if it's increasing, right, it looks like this. That's exponential growth. If it's exponential decay, it looks like this, right? And they'll use that for, like, if there's a radioactive chemical in the air and it's got a half-life, every however many years half of it goes away, it would kind of mimic this, where it's decreasing by half of its total amount each year. Now, if we have a natural base e, right? So all those were based on the base being a number, like 2 or 3 or 1.5. What happens if my base is e? Base e, right? It's increasing. We're going to look at the graph in a sec. And because what does e mean? E is this irrational number, kind of like pi, 2.718, and it's used a lot of times in population. So if you start with a certain number of people and then, like, the population grows or increases or decreases, that's what it would be like, right? And this is the fancy properties of what e is. It's the limit as my value for n approaches infinity. Okay, actually this should be an x. This should be as x approaches infinity, right? So as you increase that value for x, this number gets smaller, but then this number gets larger, and this is what kind of e is. Okay, we'll look at a graph of e to the x. Again, I had done that previously. Here's e to the x. I graphed of this. Let's do e to the x. E to the x. And there's e to the x. It basically is just like your general form equation of, like, b to the x, except this is with a very particular value. And what is that value? That value is 2.718, right? So it's just like b to the x with b equal to 2.718, and that's what we call e. Right, so just like before, its domain is all real. I could pick any number. Its range, let me just write down domain. Its range is from 0 upward, just like b to the x. It never goes below 0. It's continuous. It's increasing. It's always increasing. As you go left to right, it's increasing. It's not bounded above, but it is bounded below. At what value? At y equals 0. It never goes below 0. It's, again, as we talked about at the beginning of the year, related to the range, and that's where, like, my asymptote is, right? I have, like, a horizontal asymptote at 0. Okay, so there's a little bit about the function e, what it looks like, the graph of it. Okay, here's more about it. Exponential. Base e, a is my initial value, just as we said before, and then e to the kx. It's just kind of matching b, x, and you're just saying b is a form of e to the k. You can make them be the same thing. That's really kind of all it's saying. And what it's saying here is it's decay if your k value is negative. If this k value is negative right there. And it's growth if that k value is positive. most of the time, obviously for e, if it's not there, it's e to the first, which just means it's positive, so it's growing. Most of the time it's growth that we see with e. Not always, but most of the time. All right, so that's a little bit about what e does. Let's talk about what the inverse of e is, and we're going to play around with the logistic function a little bit after this, but we'll just kind of stop at e and logs. Exponential is obviously a function, right? We looked at this picture. It's a function. It passes a vertical line test. If we look at b to the x, right, we talked about how that's the same thing. That's also a function. Passes the vertical line test. Okay? So what about its inverse? Does it have an inverse, and is that a function? We look at the horizontal line test. It passes both of those as well, right? If we look up here, horizontally, totally fine. I have an asymptote there, but it does pass the horizontal line test. And over here, I have an asymptote horizontally, but it does pass the horizontal line test. Therefore, it is a function. And what do we call that function? A logarithmic function with base b, right? So if my function, if f of x is b to the x, the inverse is log little b here to the x. And that's something you probably have seen in your calculator, but never really used. So let's look here. This is what it means. F of x, right? So we're just calling it, it's a function, log base b of x, right? And this is like a general form, and we'll kind of see that in a sec. But basically what you want to do is take it's the opposite of exponents. So I'm going to use this phrase, I'm going to write it down, and I'm going to say it a lot. Okay? I should have done this in the general form, but log base b, I'll write it like this. I'll write it like this. B to the f of x is x. So I'm going to take this, slide this over here. Instead of writing it like this, let's write it like this, right? So here is your b, there's your base. Here is your f of x, that's what it's equal to. Logs are equal to the inverses, but they're equal to the exponent. Logs are, and here is my x, here's my x. So it's very interesting what's happening here. It's just writing it in a different way, where it's just saying your logarithm is an exponent. And that's the phrase I'm going to say often. Logs are exponents. Logs are exponents, right? So you look here. F of x is what I'm equal to. The log is equal to the exponent. The base is the number at the bottom. This is my base, the number at the bottom. And logs are exponents. So what this is saying is logs are exponents. So is equal to what? My base is 2. Okay, so 2. Raised to the what? Logs are the exponent. It's equal to, my exponent is going to give me an 8. Logs are exponents. So what is the exponent that's going to get me to 8? Well, that would be 3. My answer there is 3. Because 3 is what would go in here to give me an 8 if the base were 2. Same thing, 3. There's my little 3. That is my base is 3. Logs are exponents. So 3 raised to the what is going to give me a radical 3. You're probably like, I don't remember. Well, think about what we just did up above a little bit. What has to go in here for me to get it to be a radical 3? Well, as you remember, 1/2 is how you get radicals. 3 to the 1/2 is radical 3. So my answer here is 1/2. Logs are exponents. They're equal to the exponent. 5 is my base. Here's my 5, there's my base. 5 raised to the what is going to give me 1/25. All right, I'm on the bottom, and it's a 25. How do I get from 5 to 25? That would be a 2. But it's underneath a 1. So now it's not just a positive 2, it's got to be a negative 2, because 5 to the negative 2, 5 to the negative 2 gives me 1/25. Right? Are we following a little bit? 4 raised, right, there's my base, is my base. 4 raised to the what will give me 1. Everything that's equal to 1 is always the same. How? 4 raised to the what gives me 1. A number raised to this number always gives you 1. How do I always get 1? Well, that's if it's 0, right? Anything raised to the 0. 0 is 1. Anything raised to the 0 is 1. So, as a little aside, I could do log of anything. 10, 15, 2000, and put a 1 here, and the answer is always 0. Right? I could put whatever I want right here. But if I have a 1 right here, that's always going to mean that I have an answer of 0. Because the only way to get a 1 is if I raise it to the 0 power. Logs are exponents. Anything raised to the 0 is 1. And there's my anything. 7 is my base. A little weird. This 7, I'll highlight it to be consistent. This 7 is my base. 7 raised to the what gives me itself. 7 raised to the what gives me logs are exponents. So the exponent I would need to raise this to in order to get back to myself is a 1. Right, and you can kind of see here, this is it kind of explained out. Log base b is equal to 1 because b raised to the 0 is 1. That's exactly what I said up here. Okay, log base b to the b, if these are the same, my answer is 1. And that's exactly from this example. And then the other two are just from the examples we did. This one's a little bit weird. I'll talk about that a little bit later. But it's what raised to, b raised to the log. Basically they cancel because exponents are logs, so you're canceling it out. I think I have an example down here of it. It gets a little bit weird. But if I have, let's say 5 raised to the log 5 of 25. Right? Looking only at the exponent, right? So looking only at this, log 5, 25, is saying my base is 5. I'm raising that to what to give me a 25. Right? And that answer would clearly be a 2. Right? So now 5 raised to the 2 is 25. Right? So it's a very interesting kind of like double inverse where this 25 comes from this 25. And that's because logs are exponents. So the answer to what's boxed in red up here, is the exponent that I'm about to raise the same base to. I'm about to raise it to the same number. It's a 2. So it cancels out. Very weird. We're going to do some examples with this next time, and we'll see some more practice with that. But that's a little bit high. I'm okay if you don't get that now, but these three I would love to be kind of clear at this point. Properties of logs. It's called the common log, meaning if you do not put a base, if a base is not written, we can assume it's base 10. I don't know why they chose 10, but they chose 10. Just like if I say 3, that's really 3 to the first. Just like if I say square root of 4, that really means the index is a 2 there, right? But we don't really write it. Same thing. Log of let me do an example. Log of 100, nothing written there, would be my base right here. Base, which we cannot see, has got to be a 10. So that means 10 raised to the what gives me 100. And the answer here, answer would obviously be 2. The answer is 2. So I would say is log of 100 is equal to 2. Right? So if you do not see a base listed, the base is assumed to be a 10. Just like this. just like this, where we don't see something, we assume it means something. Same thing. X is really x to the first. Same thing, where if you do not see something listed, it's assumed to be something else. Same thing. If a log does not list anything, that means it's really a base 10. Okay, I know this is a lot, but I think the video is nice that you're able to like pause it and kind of stop and see what's going on. Oh, I actually did the first example already. So this one we know is 2 because the base is 10, and 10 raised to the what is 100. And that would be 2. Logs are exponents. I'm going to write that down again. Logs are exponents. Right, so you want to know that the answer to a logarithm is the exponent. Okay, again, no base, so I assume my base is 10. A little bit weird. 10 raised to the what is going to give me 10 to the radical, the fifth radical of 10, so that's really to the 1/5. Right, we know that, right, 1/2 gives us a square root of a number, so 1/5 would give me the fifth root of that same number. So the answer there is very simply would just be 1/5, and my answer here, right, is 1/5. Same thing, log, I don't see a base, so we assume the base is 10. 10 raised to the what is going to give me 1/1000. Again, it's underneath, so it's got to be negative. I know my answer has to be negative. And it's 10 raised to the what would give me 1,000? That would be -3. That would be what goes in here, right? So this 2 goes in there. That 1/5 goes in there. That -3 goes in there, right? Logs are the exponents. Again, we see the same example I had shown a little bit before. Looking just at the top, this. I don't see a base, so I assume the base to be 10. So 10 raised to the what is going to give me 6. Now, I have no idea what 10 raised to a number is. That's going to give me 6. I don't know, probably some fraction. Right? But if we just look at above, right, 10 raised to that number, right? 10 raised to this. This number, 10 raised to that, is going to give me, I don't know what it is, but I'm going to get 6 out of it, right? And here is the 10, that 10. 10 raised to the whatever number is supposed to go there, the answer, whatever the answer is that's supposed to go there, is going to give me 6. Well, if I raise 10 to that number, I'm getting 6. So they cancel and I get 6. There's my answer there, 6. A little weird. That one, like I said, I'm okay if you don't know that right now. We're going to see some more practice with that. But the logs are exponents. So logs are exponents. Logs are exponents. All right, do the following in your calculator. If you see, I can see, should be here, function log. Beautiful. 34.5. Okay, and I see I get 538. Okay, so log, what's the base here? My base has to be 10 because it's not seen. So what this is saying is 10 raised to the 1.538 is equal to 34.5, right? That's what that's saying. Looking at the one beneath it, 10 raised to the 1.37. Oh, wait. I just saw that. 1.37 should be 1.38, but I just saw that. That's going to be 34.5. Let's check it in the calculator. 10 raised to the 1.537, 34.43, 34.5. Off by a little bit, but they're the same, right? So logs are exponents. The exponent here, which is my answer here, I raised 10 to that. That's what I'm getting. My answer is the exponent for logs. Very interesting. All right, again, we'll just see this. Solve by changing. Come on. Solve by changing the following to exponential form. Okay, so log x equals 3. This would be, again, I don't see anything, so base is 10. 10 raised to the logs are exponents, so 10 raised to the 3 is x. Logs are exponents, so the answer is my exponent. 10 raised to the 3, well, that's clearly 1,000, and there's my answer to that. Log base 2x equals 5. My base is 2. Logs are exponents. There's my base. Logs are exponents. There's my 5 is equal to 16 times 2 is 32. So 32 is my total answer. Right? So it's just getting the hang of where things are in this log and what they mean. Logs are exponents. We'll do a couple examples, base e, and then that'll be it for now. Just like when we see log and we don't see anything written around it, we say that that's base 10. If the base is e, we call it the natural log and we use ln. So just like when we had log, no base, we said it was base 10. They didn't want to have something else and they want to keep writing e, so they just said ln is natural log. So this is important. Log base e of x is equal to ln of x. And that's the inverse of e to the x, right? Which was the exponential function. Right, here's a couple little basic properties, some simple stuff, right? Again, the exact same order as the box above, where e and ln, they cancel because they are inverses. Just like multiplication and division, they cancel, they're inverses. Adding and subtracting, they're inverses, they cancel. Right, same thing here. I'll do this in a different color. Same thing here. ln of 1 is saying, I don't see the base, so it's e raised to the what is going to give me 1. And we said every single time, no matter what, that's got to be 0. There's my answer. My result is 0. Right? If I get back out the same thing, e, my answer has to be, I have to be raising it to the power 1. Same rules as above with 10 or as any base. Okay, so here's a couple examples. I did it out partially for you. We kind of don't really need to see the log base e. I just did that just to show you a little bit. I'm going to go like this. ln, we don't see a base, so that means it's e. Like this, e raised to the what is going to give me a radical e. Just like we saw this example up above with the 10 or the one before. In order to get a radical, my answer is a half. My result is a half. Logs are exponents. Okay, log ln e. Okay, my base is e. My base is e. Okay, my base is e, and now it says, what do I have to raise it to get, as a result, e to the 5th? Well, that's kind of obvious. E to the 5th is what I want to get. There it is. What do I have to raise my e to, which you can't see, my e, in order to get an e to the 5th? Well, that's clearly just the number 5, right? How do I get e to the 5th? We'll take e, raise it to 5. E ln of 4 is 4. Again, same thing. E ln of 4. If we look just at the top, that means ln with the base, well, I'll just write here, base is e. E raised to the what gives me 4. I have no idea. But whatever number I put in there, whatever number is in there, I'll just say question mark, I'm going to get 4. E raised to question mark is going to give me 4. So e raised to, and my result is question mark, e raised to ln of 4. ln of 4 means base e. E raised to this something is going to give me a 4. I don't know what it is. I'm going to call it question mark. But that's my answer. Because logs are exponents. I take e, I raise it back to that, I'm going to get out 4. As long as this base and this number match, then they'll cancel. And we saw that up here with 10. As long as this is 10, this log is base 10, my answer is 6. There it is, my answer is 6. And I did one more up here, right? As long as this 5 matches this log base, they cancel, and I'm going to get 25. Right, so again, it is weird. I hope those 3 examples did help. We'll just do this 2 quick things, just like we just saw right here, which you can see. ln of 23.5, function ln 23.5 3.157, right? So we see this answer is 3.157, and what's happening here is that the base is e, because it's ln. So my base is e raised to the what gives me 23.5. My calculator does it for me. My answer is 3.175. So if I take e and I raise it to 3.175, e, which I gotta go to keyboard, e, and 2.174 gives it to you, raised to the, what number? 3.157. Whoops, I don't really need that. There you go, 23.49999, so 23.5, 23.5. Right, and we can see that those are exactly interchangeable. They're inverses. It's just a very weird inverse that we've really never seen. Last thing, I'll just show you the graph, and we'll call that a day. I know this is a little confusing. We're going to do some practice problems and just going back and forth between logs and inverses. Let's look at the graph. So here's a graph of log, right? Which I don't think I actually ever had you graph. There's a graph of log of x, and here's a graph of ln of x. Right, so they are very similar. It's just a matter of where do they go up to? Where do they go up to? Where's their, right? They're increasing just at like kind of different rates. This is just a little bit faster in the beginning, right? Just like we can see here, b to the x and e to the x. Right? They are really the same graph. It's just a matter of who's ahead of who. That's the same thing. Log is base 10, ln is base e, so it's just different numbers. Right, but either way, we're looking at the graph. I'll get rid of this one. Let's just screenshot this real quick. Purple graph. And there we go. Is the domain all reals? Yes, you can use any number. There is no holes in this. It looks fine. So my domain is negative infinity to infinity. Actually, sorry, my domain is actually 0 to infinity. 0 to infinity, right? I'm using the x value starting at 0 going this way. My range is negative infinity to infinity. Sorry, I mixed those up. The range is from negative infinity to infinity because I'm starting down, I'm going upwards, and I'm gradually increasing. I'm just going to keep increasing forever. Is it continuous? It's continuous, right? But only from really 0 to infinity because it doesn't ever go past 0. So it's got to be continuous on the same area as its domain because it can only use the x values. Is it increasing? Yes, it's increasing, but again, only where its domain allows, so 0 to infinity. Is it symmetrical? No. Is it bounded above or below? No, it's not bounded at all. It goes down forever, and as we said, it goes up forever. It's always increasing. There's no extrema, there's no asymptotes. There's a vertical asymptote, but there's no horizontal, because this is gradually increasing forever. There is a vertical asymptote, and we can see that where? At x is equal to 0. So although I'm continuous like excluding the number 0 because my domain starts at 0, but that's where my asymptote is. So a little bit just like we saw when we did domain and we had to exclude where my asymptote was, the same thing, and that's where I'm continuous from. It's kind of the same idea. Okay, so that's the end of that. I'll stop there. On the bottom of these, I just talked about logistic modeling for exponential functions, and that's really talking more about this function, which we have some cool facts about. But for right now, I think that's where we're going to end right there. The key is these things right here, being able to switch back and forth between logs and exponents and understanding that they are inverses.